Hi everyone. I'm re-recording by direct request a video about fun and fix for day 3. If any of the videos don't make sense or there's a part where the audio cuts out or something else bad happens, please don't hesitate to let me know. I'd be delighted to just fix it, and I'll probably do a better job the second time. So, it's a win-win for everybody. So, in this video, we're going to talk sort of in detail about anonymous functions with the fun keyword and anonymous fixed points in recursion. Let's get started. So we'll do this in a little modular playground right over here. So let's start by looking at pred, right? So this is our previous definition of the predecessor function. It's that saturating or truncating predecessor that cuts off at 0, right? So the predecessor of 0 we say is 0 because the naturals don't really have negatives. What are you supposed to do? And that's just sort of like a buyer beware kind of situation. You have to know this so that don't expect pred to sort of go down below 0 or anything like that. That's just where we stop. Okay, so I want to talk a bit about types, and then we're going to talk a bit about how coq actually represents functions and sort of what it means to have a name and so on. Okay, so there's predecessor. Just to check in about the types, pred itself is a function, so it has type nata or nat here. Make this one step bigger. So if you give it a nat, that expression will have nat. So pred5 is a term of type nat. Great. Okay, if we run it, pred5 should give us 4. But if we run pred0, these things happen. It's just to anybody. So there's another vernacular command you can give that I think is really useful. It shows you the definition of something. It's called print, and it tells you, hey, how is this defined? Not what type does it have, not how does it run, but what is it? It's a very useful command. Particularly once we go on and start doing proofs later on, to do a proof, you need to know what you're proving something about. So print will be very valuable then. Now it's a good reminder in any case. So print pred, let's see what it says. Well, let's scroll up a bit here, give ourselves a little more of this information. Great, thanks. So it says pred equals, and then it says fun n is a nat match n, and there's a definition, and then it says what type it is. Handy, right? Nice to know. And then it says argument scope is nat scope. Okay, there's a lot to unpack here. The first thing I want to note is this isn't how we defined pred, right? We wrote definition, we didn't write fun. So definition will just turn into a fun. If you have arguments, it'll be fun. It's not everybody's experience of arguments. If you have parameters, it'll be fun. So this definition up here got automatically turned by coq into this definition, saying that pred is what? Oh, it's this function, right? You'll notice up here we specified a return type. Down here, there's no specification of return type, but the type of the whole thing acknowledges that our return type above was correct. And in fact, we never would have gotten down here. The blue wouldn't have advanced this far if our specification were wrong. Okay. One other tiny note. Argument scope is nat scope. So this has to do with sort of how parsing works in coq. Like we've been able to define our own notations and do all kinds of fancy things. You've probably seen scopes talked about. These scopes are part of how coq determines the meaning of symbols, right? Sort of nat scope is a context where you expect a natural in some sense. We're not going to particularly talk about parsing or any of the details of that. coq is a very advanced and interesting parser. Later on in courses like 101, Theory of Computation, and maybe electives like mine, like Advanced Functional Programming or 131 Programming Languages, we'll talk much more about parsing. But we're not really going to bring it up again here. Okay, so that's what it is. So writing something as a definition with arguments, with parameters, is just the same as writing that definition is equal to and then writing an explicit anonymous function there. So that's an interesting idea. Every named function is just an anonymous function that's been assigned to a variable. Right? We're just given it a variable binding with definition. So then you can give sort of a general rule here that if you write definition with one parameter of type t and another parameter of type u, and you're going to return some type z, and you've written this very great expression blah that defines it, right? This is sort of meant to be schematic, right? This is some definition. This is just the same as if you had written this, which is just the same. Okay, you can leave off that return type. So these equivalences are important. They give you some flexibility. They let you sort of think about what's happening here. Right, so we can give it a sort of a general abstract format saying look, if you have this, right? Now, what does this mean? So name means like some identifier. What are identifiers? So Cock writes identifiers in snake case. Snake, whoa, I don't know. Sorry to shout. Snake case. Maybe you've seen camel case or reclining camel case, right? So Cock uses this one, and you should use it too when you're programming in Cock, sort of like a when in Rome kind of vibe. So these are all names. So what is a name? A name is like some alphabetical character followed by some number of like alphabetical characters or numbers or underscores or dashes or primes. These little ticks, all those can go in names. And then you have 0 or more arguments. That's what that star means. It's named after Stephen Colcleany, who's an important logician who came up with this notation where star means 0 or more. You have some optional return type here. And then you write colon equals an expression and then a period. And that's like, this is the format. This is the syntax of a definition. This is what it looks like. Now, a function looks like this. So fun, args plus, and then some expression. Right? So for definitions, return types are optional. For funs, they are forbidden, which in fact means I should get rid of this. You're actually not allowed to write the return type there. Right? So if this is the schema for a definition, this is the schema for an anonymous function. Right? So there's some difference. There's no name, right? It's anonymous. You have to have some arguments. Otherwise, like, what's your function doing? But then you have the expression part here. Okay. So let's put this into practice. This is, I think, a great class of exercise. How would you write the function negb that takes a Boolean and negates it using an argumentless definition in an anonymous function? Write down every type you can. So writers of prose, fiction or nonfiction, do exercises like this where they like you'll express an idea one way and they'll say, okay, great, write it another way. You know, put it in passive voice, put it in someone else's words, put it in like a different style. And these are ways of stretching yourself. And I think that's a really great way to practice to make sure you understand everything. Is to write a program one way and then be like, oh, well, how would it look this other way? But you want maximum flexibility. That's going to make you the best programmer you can be. Okay, so let's try it. So definition negb. Okay, so if we're going to write a function, let's write it transformationally. So I'm going to write just like sort of the silly way of doing it. Okay, b bool. If b, then false, else true. Okay, great. Now that's the original negb orig, classic flavor. So let's just transform it. So what did we say how it works? So this will turn into an argument to an anonymous function. We won't need to write the return type, but we can write. But here it says write down every type you can. Okay, so we should write the type of all of negb there, and then the body should stay the same. So the transformation will look like something like this. Okay, negb is gonna be a bool or a bool function. We're gonna take b as a bool. We're not allowed to write the return type here, and now we write the body. Right, so this is, I think, sort of the gold star answer here. It's okay if you wrote something like this. Okay, it's generally not great style to write this all in one line, right? It'll be, I think, a little bit nicer to write something like this. I just realized I'm not in keycast mode. Which isn't working for some reason. Let's leave it. Okay, so this is also a fine way to define the function. For booleans, I like if a little better. This is really noisy compared with the if b then false else true. Okay, what about recursive functions? How does that work? Well, we saw even b prime. Let's look at the double function, right? We saw even b prime at the end of day 2. Let's look at double. So here's a recursive function. Let's see what Coq says when we print it out. Huh. Interesting. So like, we saw the fun keyword before, where you'd write fun, blah, blah, blah. Now it says fix and then the name of the same function. And then an argument, and then a return type. And then rather than the arrow, it's a colon equals. Okay, the syntax is just like a little different. And then the body of our function, and then its type, and then some weird crap about scopes. Okay, so this is Coq's internal representation of functions. Just as there's anonymous plain functions, there's anonymous recursive functions. Okay, they're like not exactly anonymous, they're like pseudonymous. Pseudonymous? How do people pronounce that word? I think I've only ever read it. Having a pseudonym. A pseudonym means a false name. Pseudo false name. Uh, so here we're saying, okay, I'm going to define a recursive function. That's what fix means. Here's its name. It's called double. Now I can bind this to a variable name other than double. We'll see this in a moment. It takes one argument, n is a nat, and it returns a nat. Here's its definition. Match n with blah, blah, blah. And then, because I've said it's going to be recursive, I can use this name that I set up over here. Okay, so here's the equivalence, right? If you write fix point, name, one or more arguments, fix points always need arguments, and then a return type, colon equals expression. You could have just said definition name. You could have just defined the name and said fix, and then written the name you had, and then your arguments, and then written a return type. Okay, you're allowed to here, and then the colon equals expression. Okay, so let's write triple two ways, once using fix point, and once again using definition and fix, writing every type we can. Pause the video if you like, see where you get. Okay, here's the answer. So we can follow the same pattern of double. So we could write something like this. We check our work. Beautiful. Okay, here's another way to do it. So how did this work? That's what I wanted. So it was Control X3 to do that little buffer split. So we're going to take this into this. Triple prime. So I'm going to write the type. It said write every type you can. This is going to be type nat to nat. And it says fix triple prime. I'm going to use the same name for now. N is a nat. Return a nat. Match n with O goes to O. S of n prime goes to S of here. Well, mix it up. 3 plus triple prime n prime. Right, why not? Save ourselves the S's. Use them for something else. Okay, and we can check this. A couple things to watch out for. A super common mistake when you're defining multiple versions of functions is to accidentally refer to an earlier one. And this will actually work fine because triple and triple prime do the same computation. It doesn't matter. But it's not doing what you think it does. So here's another thing you can do. You could write a function like loop. Neat. Another syntax you could use. So what I want to draw attention to here is, look, I locally named this fixed point something else. I called it loop, which is what it's doing, right? It's looping, right? It's not like a for or while loop. It's a different kind of iteration or looping, but it's looping. And then I said, okay, that recursive function, we're going to call that one triple prime. So the definition is really just about assigning a global name to some expression you've given. And then fix lets you say, okay, locally, I've got this thing that's recursive and I'd like to sort of call it by this name here. Okay, hopefully I was audible and I was also clear, and that was helpful. If you have any questions, please feel free to post to Piazza. If there's any other accessibility issues, please let me know. So one thing I probably will start doing is posting videos to YouTube because they have an automatic captioning algorithm. And I think it doesn't do a great job, but it's better than nothing. That way it'll just be available to y'all, and then I guess also other people in the world, which is good for better or worse. Okay, great. I'll see y'all in class today, and really not too long. Hope everybody's doing well. You should have your grades from day 1 already, and day 2 grades will be coming at you shortly. All right, cheers, y'all.